Military planners in the post-war period were consumed by the threat of nuclear war with the Soviet Union. The Arctic approaches over the North Pole could allow for long-range bombers carrying nuclear weapons to attack North America. As a response, the Canadian government invested heavily into our national air defense and initiated a series of innovative programs. Most notable of these were the CF-100 Canuck and the CF-105 Arrow interceptor projects. While nearly forgotten today, these aircraft were to be complemented by an indigenous guided missile design called the Velvet Glove. The Velvet Glove missile would dramatically increase the lethality of the new Canadian interceptors in the face of Soviet aggression. Though it never saw active service, the missile remains an achievement easily overlooked in our collective history. Post-war Canada experienced a growing threat of Soviet aggression. Russian armies stood poised to invade allies in Western Europe, and by 1949, Russian scientists had detonated their first nuclear bomb. Soon after, it was sufficiently miniaturized to equip long-range bombers and threaten Western powers with a devastating attack. This was the start of the Cold War, in which the Western and Eastern powers faced off against each other for over half a century. The Canadian response plan was this. Attacking enemy bomber formations would first be identified by ground-based radar stations of the Distant Early Warning Line, Mid-Canada Line, and Pine Tree Line. Day fighters like the CL-13 Sabre would then be vectored onto the target. After visually locating and identifying the bombers, they would then maneuver their aircraft to bring it down with a burst of machine gun fire. More advanced fighters like the CF-100 Canuck could identify the target in all weather and maneuver in behind them using their onboard radar sets and fire control computers. Initially, it was expected that guns would be sufficient to shoot down the large bombers, just as they had for most of the air engagements in World War II. With the introduction of jet combat aircraft starting in 1945, the nature of aerial combat was changing. Closing speeds increased dramatically, and the time pilots had to identify, react, and engage enemy planes was decreasing rapidly. In addition to this, the speed and altitude performance of bombers was improving, and doubts were raised about existing weapon systems and bringing them down. Studies of aerial combat in World War II confirmed the deficiencies of the gun approach. It was noted that multiple passes had to be performed before the bombers could be brought down. This was becoming increasingly more hazardous, and so it was decided to push for a one-pass solution. To achieve a higher kill rate with guns, two aspects could be refined. Some American and Canadian fighters favored increasing the rate of fire by adding more guns. Sabres were equipped with 6 of the ubiquitous Browning M3 12.7mm machine guns. The larger Canucks were equipped with a bank of 8. Alternatively, some British-built fighters like the de Havilland Vampire favored a strategy to increase the weight of fire by using larger caliber rounds fired from slower-firing autocannons. This approach sacrificed the overall rate of fire to maximize the impact of each round. The larger 20mm rounds carry more kinetic energy than the smaller 12.7mm machine gun rounds, and thus cause more damage with each hit. The available ammunition supply was also a critical consideration. Smaller caliber guns could carry more rounds than the more damaging larger caliber guns. The rate of fire combined with the ammunition supply translated into the so-called trigger time. The longer a pilot could deliver rounds on target, the greater the chance of a hit and a kill. A practical limit was reached where adding more guns and ammunition would start to severely impact the performance of fighters. The weight and volume of systems in both approaches became unmanageable. Early models of the Canuck initially followed the standards set out in World War II, while further evolutions of the plane moved away from guns and incorporated new technologies to increase their lethality in the face of a more sophisticated threat. Starting in the late 1940s, the Americans developed the 70mm folding fin aerial rocket system, commonly called Mighty Mouse, to address the shortcomings of the gun systems. The innovative rocket system overcame the two deficiencies of using guns. The rate of fire was high due to the pod launch system, and the weight of fire was high due to the large diameter and explosive warhead of the rockets. The rockets themselves were 70mm in diameter and 1.2 meters long. They weighed 8.4 kilograms, including a 2.7 kilogram high explosive warhead. Folding fins at the rear extended upon launch and provided spin stabilization. However, even with stabilization, the rockets had intrinsically low accuracy. This is why large numbers of rockets were launched at once. Interceptor aircraft typically carried multiple pods, each containing dozens of rockets that could launch a salvo shot in less than a second. The rocket firings were precisely aimed and timed by the use of a radar and fire control system incorporated into the aircraft. A hit from any one of these would cause significant damage to the target aircraft and hopefully bring it down with the first pass. They had an effective range of 3,400 meters. The system was designed to put up a wall of explosive projectiles through which the bomber had to fly. While an improvement on the older gun systems, the rockets were not without drawbacks. The unguided rockets necessitated launching in one large volley. Once its rockets were expelled, the fighter would have to land and reload before it could once again pose a threat to further enemy intruders. This weapon system was adopted by the CF-100 Canuck Mark IV and Mark V fighters serving in Canadian frontline squadrons starting in 1954. It was also the system used by American-built fighters like the F-86D Sabre Dog, the F-89 Scorpion, and the F-102 Delta Dagger. These fighters were maximized for intercepting long-range bombers at the expense of their dogfighting capabilities. A drastic alternative to firing large volleys was to launch only one with a warhead so massive that the poor accuracy of the system wouldn't be an issue. The Genie was an unguided rocket armed with a 1.5 kiloton nuclear warhead. This warhead would create a 300-meter diameter blast of extreme heat and wind that would destroy any aircraft caught within it. The system was only tested once and thankfully never used in combat. Canada adopted the Genie to arm its CF-101 Voodoo interceptors from 1965 to 1984. Though the weapon systems were going through major changes, the interception techniques learned in past conflicts were maintained or refined. Generally, an interception would begin far outside of visual range. Ground radar stations picketed across the Canadian and American landmass would detect the bombers as they crossed over the pole. Fighters stationed across the country would scramble and be vectored to the target by ground stations until visual or radar contact could be made. The interception will exploit one or more of the following techniques to win the engagement and bring down the enemy bomber. The tail chase attack involved getting in behind an enemy. This approach had many advantages and remains a favorite tactic today. Closing speeds are lower, which provided a greater amount of time to engage a target. Evasive maneuvering by the defending aircraft is also less effective as the faster turning interceptors can easily follow and press the engagement. Fuel use is a consideration in this approach. Getting in behind a target and catching up to it consumes fuel and reduces the time interceptors can spend engaging the target. The effective range of the weapons is reduced due to the relative speeds of the rounds, airspeed, and target speed. This requires that the interceptors get close to the target. Russian bombers like the Tu-95 Bear had a tail gunner to dissuade attackers from taking advantage of this approach. The gunners benefited from increased effective range and easier tracking. To overcome this formidable threat, fighter pilots developed new attack techniques. Naturally, the head-on attack was an option. Here the bombers had no defenses, and the weapon range advantage swings back in favor of the attacker. Fuel usage would also be minimized, as the interceptors would simply fly directly towards the incoming aircraft without the need to maneuver around and match speeds. This approach was safer than the tail chase, but it was not without its limitations. The development of the post-war bomber centered on increasing speeds. The Tu-4 Bull had a cruising speed of 558 km per hour, while the more advanced bombers like the Tu-95 were approaching transonic speeds in excess of 925 km per hour. This meant that the closing speeds for a head-on engagement were becoming unmanageable. Aircraft like the CF-100 Canuck were equipped with fire control computers to precisely fire the rockets in this type of approach, instead of relying on the pilot's reaction times. An alternative to both the tail chase and head-on engagements was to attack from the top, bottom, or sides. This was known as a collision course attack. It involved all the same features as the head-on engagement, but had a number of advantages over it. The closing speeds were reduced and the weapons maintained their effective range. The main disadvantage of this approach was the precise timing required for a hit. Like with a head-on approach, a radar and fire control computer was required to provide range and timing information to the pilot. Scientists working for the Canadian Armament Research and Development Establishment, or CARDE, began investigating more powerful guided alternatives to enhance the capabilities of the RCAF. The concept of guided missiles goes back to the interwar years, but the technology necessary to realize them didn't come into existence into the late 1940s. CARDE was initiated to maintain the expertise in military technology acquired during the Second World War. Starting in 1951, the Canadian government officially initiated a program called Velvet Glove to develop a guided missile to equip its Canuck squadrons, as well as the planned CF-105 Arrow. The missile attempted to overcome the deficiencies of the rocket systems already being used or in development. The large weapons could carry a potent warhead over a significant distance. This dramatically increases the chances of a kill with a single hit. This allowed aircraft carrying multiple guided missiles to engage multiple targets before having to head back to base to reload, thus maximizing their efficiency. This would also allow the RCAF to reduce the number of aircraft it operated without sacrificing capability. The guided missile program was selected because of its high level of technical complexity, while still being attainable due to its relatively low sophistication. The primary focus of the missile project was meant to train Canadian scientists, engineers, and industrialists in new defense technologies. The approach intended to maximize technology transfer to private industry, in order to support and promote the high-tech sector of the Canadian economy. There were a few different approaches towards this goal that could be employed. The most basic way to guide a missile was to use a radar set on board the attacking aircraft to send command information to the missile's guidance system. This was known as beam riding. The problem with the system was accuracy at long ranges. Due to the nature of electromagnetic radiation, the radar set loses precision with distance. Beam riding missiles could also easily be defeated through jamming and evasive maneuvering. This approach was used on early missile projects like the American Sparrow I and the British Fireflash. Scientists at CARDE felt that this approach was insufficiently accurate and robust to provide a reliable weapon of war. The Canadian military gained the Sparrow Corporation APG-30 X-band radar with the introduction of the Mark III Canuck, and proceeded to apply the technology towards their guided missile project. It was decided that a semi-active radar type seeker would be employed for the Velvet Glove. The attacking aircraft would lock its radar onto the target and fire the missile. The missile would then follow the radar signal that reflected off the target aircraft using an onboard X-band pulse passive radar receiver. The internal guidance system would then provide control information to the missile's autopilot to make the interception. This system corrected some of the deficiencies of the beam riding approach. Unlike the beam riders, the accuracy of the missile would actually increase as it closed with the target. While this was an improvement on older designs, the attacking aircraft would still have to keep the target locked on with its radar until the interception was made. This alerted the bomber to the attack and exposed the position of the attacking aircraft. The Velvet Glove was fairly large for its time, measuring 3.25 meters long and 20 centimeters in diameter. It has a traditional cruciform layout for its fins, whose span is almost 1 meter across. The missile had a weight of 144 kilograms before launch. Its 32-kilogram rocket motor could carry it approximately 8.5 kilometers at speeds ranging from Mach 0.85 up to Mach 2.3. Once it reached the target, it would detonate a 27-kilogram high-explosive warhead using a proximity fuse. The fuse was developed by CARDE's sister institution called the Defense Research Telecommunications Establishment, and it was ready for use by 1955. It used a microwave emitter to calculate the range to target and detonate the warhead at the appropriate time. The technology was then transferred to Westinghouse, Canada for application and further refinement. The development of the missile was conducted from 1951 to 1956. During that time, between 130 and 300 missiles were manufactured by Montreal-based Canadair and fired for testing and evaluation. The development team decided to use a gun system firing Sabre shells containing Velvet Glove models instead of an expensive supersonic wind tunnel. The innovative high-low chamber design allowed models to be accelerated relatively slowly. This avoided damaging them while still achieving the high speeds necessary for proper testing. This both lowered production costs and further developed expertise in the field of advanced gun concepts. Later, this technology would be applied to the High Altitude Research Project, where large gun systems were used to explore the ballistics of space re-entry vehicles without the use of comparatively unreliable rockets. CF-100s based at the RCAF base in Trenton, Ontario, began carrying out air launch testing over the nearby Picton Range starting in 1954. While these tests did show that the missile worked, it also exposed some of its deficiencies. The missile was found to be unsuitable for supersonic launches, and due to its basic design, lacked further development potential. For this reason, the missile was no longer considered for the upcoming Supersonic Aero Interceptor project. It could only be effectively launched from the slower CF-100s. Unfortunately, due to its slow development cycle, the missile was still in development when production of the Canuck stopped in 1956. Introducing the missiles into service would have required extensive refits and modifications of existing airframes. The cost of doing this was prohibitive, considering that the Canuck was slated to be replaced within the next few years. In 1956, the Government of Canada cancelled the Velvet Glove program, citing concerns over its supersonic capabilities, cost, and the perceived lack of effective range. Military planners discovered that the missile would only be effective against the now obsolete Tu-4 Bull bomber. Another consideration was competition from a few promising American designs like the Falcon and the Sidewinder. The nearly 400 engineers and scientists tasked with the Velvet Glove were transferred to other programs in order to preserve the expertise within CARDE. The ideal guided missile would autonomously guide itself to the target after being launched by the attacking aircraft. This is known as fire and forget capability. The advantage to this approach is that missiles could be fired at a target while limiting exposure of the launching aircraft in terms of radar emissions and retaliation attacks. There are two main types of fire and forget missiles: those using an onboard radar and those using an infrared seeker. Active radar type seekers are the most complicated design, but also hold the most promise in terms of capability. The Canadian government recognized this and began collaborating with the United States on their Sparrow II missile system. The Sparrow used an onboard K-band radar transceiver. Once locked onto a target, the missile would ignite a 35 kN engine and bring the weapon up to Mach 2.5 in less than 2 seconds. The radar would then track the aircraft and guide itself with an onboard autopilot. A proximity fuse would then detonate the 20-kilogram warhead, destroying the target. The complexities surrounding miniaturizing the radar and computer systems presented a significant challenge for its day. The K-band radar also proved problematic, and tests of the system weren't promising. The Americans cancelled their part in the project in 1956, and the missile was transferred to Canadair for further development. The Canadian government was trying to arm their upcoming fighter with a domestically developed and manufactured missile. Canadair spent another 2 years working on the design, but in 1958 the Canadian Sparrow was cancelled. 1958 was also when the Avro Arrow took its first flight. There had been substantial controversy surrounding the armament of the cutting-edge aircraft from the initiation of the project in 1953. Proposals to arm the Arrow included all combinations of available weapon systems, including guns, rockets, and guided missiles. The Arrow could be equipped with 4 30mm cannons with 200 rounds each and 56 70mm rockets, or 4 Velvet Glove missiles, or 4 Sparrow II missiles. With the cancellation of the Velvet Glove and later the Sparrow II, the Canadian government had to look to foreign designs to equip the Arrow. The United States were developing the Sidewinder, Sparrow III, and Falcon missiles, while the United Kingdom were developing their Fireflash, Firestreak, and later Red Top missiles. The final proposal to arm the Arrow consisted of 6 American-designed Hughes Falcon guided missiles plus 24 70mm rockets. Importing the Falcon was tempting, as it would further enhance the capabilities of the Arrow beyond what was available through Canadian designs. The Falcon was available with 2 types of seekers: semi-active radar and infrared. Infrared seekers were promising because of the relative simplicity of the design and their effectiveness against modern jet aircraft. The drawback to this design was the limited engagement angle. The missiles required that the enemy plane expose its hot exhaust gas to make the seeker effective. Head-on engagements would provide an insufficient signature for the missiles to follow. Because of this, tail-chase engagements were most effective. The United States started development of their Sidewinder missile in 1946, and it began active service in 1956 after a long development cycle. The British were also developing their own rear aspect IR missile starting in 1951 called the Firestreak. It was introduced into active service in 1957. This was followed by a more capable all aspects IR missile called the Red Top, whose development started in 1956. Infrared seeker-type missiles didn't enter service with the Canadian military until the arrival of the Falcon C missile, with the purchase of the CF-101 Voodoo interceptor. Today, the CF-188 Hornet is equipped with a mix of fast-firing 20mm gun, ground-attack 70mm rockets, and air-to-air missiles based on the Sparrow design, as well as the heat-seeking Sidewinder. The legacy of the Velvet Glove and Sparrow missile projects persists. They represent a milestone in the Canadian aerospace industry. The programs trained a generation of Canadian scientists and engineers to take on the challenges of our increasingly technologically driven world. Although they never saw active service, the legacy of the program lives on.